Hello and welcome to AP Stats. This is 9.1. We're going to take a dive into something called a confidence interval. So let's recap what we've learned in Chapter 8. Technically, we're going to do 2 chapters in this little unit. So recall the general properties of these sampling distributions. For samples, we have faith that the average of the samples will be equal to the true proportion, right? Because samples have variability. Some samples will come back with a sample proportion of greater than what it actually is. So with Indiana and Democrats, the proportion of Democrats in Indiana might be, suppose it was 50%. We could get a sample that comes back as 60%. We could get a sample that comes back as 40%. But in the end, if we take a lot of samples, in fact, if we take all possible samples of a certain size, they will cluster around 50%. They should. We have faith in our samples. That's what that says right there. 10% rule. If the 10% rule, then the plus or minus of our samples will be given by this equation right here. The standard error or the standard deviation of our samples. This is the plus or minus. So if we take a sample, it should be right around that, plus or minus that. And you can tell that this is affected by the sample size. The larger your sample size, the closer your samples will be together, is what this is saying. And also P does determine how close the samples will be. The closer you are to 0.5 for the true proportion, the more variability you have, or you could have. So there's a little dance here with N and P. And then if the large counts condition is satisfied, if you remember, NP has to be greater than or equal to 10, and N times 1 minus P has to be greater than or equal to 10. If that condition is satisfied, then we can use a normal distribution for our samples. We can set up our samples with N mu like that, and use norm CDF and stuff like that to find probabilities. All right, first example, you can read, pause, and read, unpause. All right, you read part A. The Doolin administration is considering shutting down the school. If they make a simple random sample of size 100, and the sample comes back as 9% positive or more, they will shut down. Now, the sample should come back as 9% or more, because we know, we are statistics gods, we know the 10%. We know that in reality, 10% of the 2,000 students have active COVID, but the administration doesn't know that. All right, so what they're saying is that they're gonna take a sample, and if it comes back as 9%, so they're even giving it, that's what they're saying, if it comes back as 9% or more, they'll shut it down. All right, so let's look at what our samples should look like. Under the assumption of 10% positivity or active COVID, our samples will cluster around 10%. That's what should happen. 100 of 2,000 is less than 10%, so 100 is less than 10% of 2,000, so check. That means we can find our plus or minus, so our samples should come back clustering around that, plus or minus about that. So in fact, 68% of our samples using the empirical rule should be within 0.03 of 0.10. So the majority of our samples should come back as between 0.7 and 0.13, the majority. All right, then because our sample is large enough, using the NP, and then it turns out that we can use a normal distribution to find this probability out. So if we set up a normal distribution and we look at 0.09 and above, and we use the norm CDF, we get that this area is 63% roughly. So 63% of all the samples that could possibly be taken of size 100 will come back as 9% or greater. Okay, so more than likely, CHS is going to take a sample and it's going to come back as more than 9%. We're going to have to shut the school down. We're not guaranteed. Let's keep reading. Now, as I work through this video, obviously pause, write down as you need to, rewind. It's nice, actually. A video actually works really well. B. Okay, so the administration did take a sample of 100 students, and 8 were found to have active COVID-19. Uh-oh. 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 Because that's a sample of 8%, which means they're not going to shut the school down. When in reality, it's a 10% active rate. But we know that coming back as greater than 9% is only 63%. So there was still a chance that a sample was going to come back less than 9%, and that's what just happened. Just by chance, our sample came back less than 9%. So this is an error. In reality, we should have shut down, but we did not. Our sample came back as not shutting down. All right, so should the school shut down? Well, even though the school should shut down, because in reality it is 10%, which is greater than 9%, based off of the sample, which is 8%, which is less than 9%, the school will not shut down. And people might get sick. That's unfortunate. Knowing that samples have variability, the AP Stats teacher is a little concerned with the conclusion, because just one sample, right? You don't really want to make a conclusion definitively based off of a sample. We don't want to say that because the sample came back as 8%, that means that the positivity rate of the high school is 8%. You see the problem there? We don't want to do that. What would be better is if we constructed something called a confidence interval. Let me explain. So what could happen if another sample was conducted? If another sample was conducted, we know that, well, these people don't know, but we know, because we're the statistics gods, and we know the 10% proportion. We have shown that 63% of samples will show an active COVID proportion of at least 9% and will result in shutting down. We just got lucky, maybe unlucky, and got a 0.08. All right, so what should happen, the stats teacher says, instead of estimating an exact value, instead of taking a sample and the sample coming back and us saying the exact value of the number of active cases is 8%, what we should do is do a confidence interval. We make an interval that has a high probability of capturing the true proportion. This is called a confidence interval. Now, a confidence interval is a point estimate, which comes from a sample plus or minus a margin of error. So what we should have done is taken our sample and came back with a 0.08 plus or minus 2%, maybe, plus or minus 1%. All right, so this margin of error is an important thing in inference in statistics. It's the plus or minus. So how do you find that plus or minus? We know how to find a point estimate. A point estimate is just whatever your sample is. Sample proportion, sample mean, whatever it is. And then your plus or minus is a little bit harder to find. So let's investigate that. Okay, first thing in a confidence interval is a point estimate, which we talked about. A point estimate is considered a statistic because it comes from a sample. It's an estimator of a parameter. So the sample proportion estimates the true proportion. The value of the sample proportion provides an estimate of the population proportion, okay? So suppose that the true proportion is 0.10. If our sample comes back as 0.12, then it's off by 0.02. That's the error of that sample. If it comes back as 0.07, then the resulting is an estimation error of 0.03 because we're comparing to 0.10. All right. Different samples come back with different errors. Sample variability. That's why we can't use a sample to state definitively, for example, that the active number of cases was 8%. We need 8% plus or minus would be a better way of stating that. Now, the margin of error, here it is right here. This is the margin of error of a statistic is the maximum likely estimation error. The maximum likely. It is unusual for an estimate to differ from the actual value by too much, by more than the margin of error. When the rules, so rule 1, 2, and 3 for sampling distributions are met, we can use the normal distribution to find margin of errors. This is broken down into, this is called a critical value. It's the first time we saw that. It's called a critical value. I'll explain what that means in just a moment. Critical value, margin of error is your critical value times your standard error. And we use p hat in here for this calculation and the sample size. We'll do some examples. It should all come together. Now, this critical value comes from a normal distribution. It's called it's like a z-score kind of. It's a z in that it comes from a normal distribution. Z always comes from normal, and then later we'll get a t, which will come from a t distribution. So z is from a normal distribution. Okay, so we're going to be asked to find like a 95% confidence interval or a 90% confidence interval or something like that. And the z-score will determine, the critical value is determined by whatever confidence level you have. So for example, this is a 95% confidence level. So for example, we'd be 95% confident that the number of active cases is 0.8 plus or minus maybe 2%. I don't know. I didn't calculate that yet, but here's how you find the z here for your calculation. You take a normal distribution, standard normal, like this, centered around 0 with a standard deviation of 1, and then we want 95%, so we want the middle 95%, which means you have the tails of 0.025 and 0.025, thus making 95% in the middle. Then you go into your calculator and you do inverse norm. You do inverse norm with not 95%. You do inverse norm with this number right here, the tail, and that will find that number right there. And then because there's symmetry, you can just do the positive and get that value right there. So 95% means a z critical value is equal to 1.96. And it doesn't matter if it's plus or minus because there's a plus and minus right here, and that will take care of plus or minus. So you can just put in 1.96 into the calculation for a confidence interval. All right. So what I want you to do is we're going to do a couple on our own. We're going to find the z critical value for 90% and 99%. So ideally what you do is you maybe watch me do this one and then pause it and do this one on your own. Okay, so find the z-score corresponding to a 90% confidence interval, which means you're going to set up a normal distribution. You're going to do the middle 90%, which means your tails are 0.05 and 0.05. That makes 100% total right here. So my tail is 0.05, so I'm going to use inverse norm in my calculator. Go into distribution, and don't plug in 0.9 for your area. You want inverse norm always works. You'll find this number by plugging in the area to the left. So you're going to plug in 0.05, 0, and 1, and that'll give you that. So that is the 90% confidence interval critical value. Does Same thing with 99%. You want the middle 99%, which means your tails are 0.005 and 0.005, thus making 100% total. Do inverse norm with 0.005. You can see my z-score, or my critical value, is 2.576. All right. And you can see there's a little pattern here. 90% was 1.6. 95% was 1.96. And 99% was 2.576. The more confidence you have, the wider your interval will be. That affects this number, which overall affects your margin of error. We're going to get more into that tomorrow and how these are different from each other. Okay, now on to putting it all together a little bit. We'll do some examples. It'll come together in the example. Estimating a population proportion P from a sample proportion P hat. It's done all the time. Appropriate when the following conditions are met. 1. The sample is random. The sample is a random sample from the population interest, or the sample is selected in a way that it makes it reasonable to think that the samples are representative of the population. That's the important part. If I could sum it up in a couple words, the sample must be representative of the population. So you have to be careful about how your sample is obtained. You could use a simple random sample, usually simple random sample. They'll say a simple random sample, like we'll see in an example. They should say a stratified random sample, but anyway, the sample has to be representative of the population. Otherwise, there'd be a bias, and our point estimate would be off. Number 2, sample size is large enough. This condition is met when this is true. So now consider your sample. N times P hat has to be greater than or equal to 10. N times 1 minus P hat is greater than or equal to 10. Because we won't know P anymore. We don't know the real pop. We're no longer statistics gods and know the true population parameter. We'll have to base off of a sample. And then there's technically a third one, that's the 10% rule. The sample has to be small enough as well. I don't know why I didn't put that in there. When these conditions are met, we can calculate this. We can use this. Now, a confidence interval, here's the script. Here is the script. For a confidence interval, there's confidence interval and there's confidence level. We got different scripts. Stick to the script and you will be fine. For a confidence interval, here's the script. We say we are 95 or 90% or 99%, whatever they ask us. We are blank percent confident that the interval from blah to blah captures the true proportion, and then you give context. Context. Example, we are 95% confident that the interval from 62.4, I'm just making this up, to 67.5 captures the true population mean height of women in the town. It's just an example. And then there's confidence level, 90%, 95%, 99%. So blank percent of all samples in blank percent, the resulting confidence interval will contain the true, and then give context. So for example, in 95% of all samples, the resulting confidence interval will contain the true mean height of women in the town, just for example. We could do one with my age, just for example. What's a confidence interval in my age? All right, so Mr. Smith's age, what am I? What do you think? Am I 20 plus or minus 2 years? Probably not. Am I 30 plus or minus 2 years? Am I 40 plus or minus 2 years? Am I 35 plus or, hopefully you don't say 50 plus or minus 2 years. Let's say, and which one are you more confident in? Are you more confident that I'm 35 plus or minus 2 years or 35 plus or minus 10 years? Probably more confident in the plus or minus 10 years, because the larger the margin of error, the more confidence you have. Keep that in mind. The larger your margin of error, the more confidence you are in your margin, in your confidence interval. Okay, let me show you using this app what is technically happening. So I'm going to transition. Here we are. Hopefully my internet stays up and working. So I'm setting this to, for the first problem, the true proportion of active COVID-19 cases was 10%. Let's say we want to do a 95% confidence interval with sample size 100. Okay, so we're going to make a sample. So here's a sample. Our sample came back as 11% plus or minus 6%. That's our confidence interval. So we're not saying that the exact proportion is 11%. We're saying that the proportion, the true proportion will be, we're pretty confident that the true proportion is 11% plus or minus 6%. And it captured it, all right? So 10 was in that interval. This is our interval, 11 plus or minus 6. And we did good. That first sample was good. It captured the true proportion. Let's do another one. Is our second sample good? Ah, good. Our second sample came back as 12% plus or minus 6. Ooh. Our third sample came back as 8% active COVID plus or minus 5%. Now, is it guaranteed? Oh, look at this one. This sample did not capture the true proportion. Ooh, see? It's outside of the green line. The green line, the true proportion is 10%. This confidence interval did not capture the true proportion. But we're not saying that every sample is going to capture it. We're saying that we're 95% confident that the samples will capture the true proportion. And what that means is if we do 100 of these, more than likely 95 out of 100 of our samples will capture the true proportion. So let's do it. How am I doing? Most likely all of my samples are capturing the true proportion. I'm up to 75 and I'm at a 96% capture rate. 96% of my proportions so far have captured. It should be 95. I can do 25 here. Ooh, now I'm down to 94. I didn't hit on a couple of those, so now it went a little lower. So 94. But in the long run, what's gonna happen is that if I keep taking samples, 95% of the samples should hit the true proportion, should be containing that green 10% mark. That's what's happening. All right, back to the notes. All right, we are on to the next page. Here we go. Let's do an example. Based on a representative sample, that's condition number 1, of 511 U.S. teenagers from age 12 to 17, International Union Research estimated that the proportion of teens who support keeping the legal drinking age of 21 at the following. This is what our sample came back as. Our sample came back as 64% of U.S. teenagers 12 to 17 support keeping the legal drinking age at 21. Should we say from that sample that that is the true proportion? No, because samples have variability, so we understand that. It may be higher than that, it may be lower than that, but more than likely, hopefully, this is a good sample. All right, check, compute, and interpret the confidence, change that to confidence interval. I meant to say confidence interval at the 95% confidence level. Okay, so if you go into your formula packet, take a look. We do get a little info on a confidence interval. A confidence interval is a statistic plus or minus critical value times the standard error of the statistic. So for us, What we are estimating is a proportion. So our statistic will be our sample proportion. Statistic always comes from a sample, remember? Critical value for this particular problem will be a z critical value, because it's a proportion and we're doing normal distribution, a z critical value of 95% for this problem. 95% is usually the standard. The standard error of the statistic is, well, let's turn the page. Now we're on to the second page. Ooh, fancy. We're doing one population, p hat, and the standard error of a sample statistic is right there. So we can put this all together and come up with, back to right here. Here's our, this is what we, on the page we just did. This is the point estimate, sample, z-score, standard error of a statistic. That is what we're going to use to make a confidence interval. All right, so confidence interval, statistic plus or minus critical value times the standard error. Statistic plus or minus critical value, z in this case, plus or and then your standard error right there came straight from the formula packet. If you understand, you can get this straight from the formula packet. So for us, our p hat, our point estimate was 0.64. The critical value is 1.96. You can see that on the previous page for the 95% confidence interval, 1.96. And then this is our standard error, 0.64, 1 minus 0.64 over 511. So therefore we get a confidence interval of 0.64 plus or minus 0.04. So roughly this is what we get as our confidence interval. 0.64 is the middle. If you subtract, you get to 0.60, and if you add, you get to 0.68. And then we interpret it. So what this means, what this implies, is even though our sample came back as that much, all right, we know that there's variability, and our next sample probably is not going to come back as that much, and the sample after that is probably not going to come back as the same proportion. However, what we can say is, get back out to the previous page, we can say we are 95% confident that the interval from, what was it, 0.6 to 0.68 captures the true population proportion of, now give context, true population proportion of U.S. teenagers aged 12 to 17 who support keeping the legal drinking age at 21. Let me say that again. We are 95% confident that the interval from 0.60 to 0.68 captures the true proportion of U.S. teenagers aged 12 to 17 who support keeping the legal drinking age at 21. You would have to write all of that if this was a free response question. There we have it. We just made a confidence interval. We know that this isn't 100%, but we're pretty sure that this will capture the true proportion. This is not the true proportion, but we're pretty sure that this interval captures the true proportion. The true proportion might be as low as 0.60. It might be as high as 0.68. We don't know, but we know it's in here somewhere. We're pretty confident it's in there somewhere. It might not be in there, but we're pretty confident it's in there, is what we were saying. All right, we're gonna skip example 3. Let's go to example 4. Okay. Pew Research Center quiz a random sample of 1,006 U.S. adults on their knowledge of science. One of the questions asked, which gas makes up most of the Earth's atmosphere? Hydrogen, nitrogen, carbon dioxide, or oxygen? A 95% confidence interval for the population, for the proportion who would correctly answer this nitrogen is 0.175 to 0.225. All right, not very good, is it? All right, that's less than a quarter. They had 1, 2, 3, 4 options. and less than a quarter of them, well, this was our confidence interval. So as low as 17%, roughly, and as high as 22% answered this correctly, which is not very good for US adults. Anyway, interpret the confidence interval. So there's our confidence interval right there. Is what this means. We can interpret it. Here's our script again. We are 95% confident that the interval from 0.175 to 0.225 captures the true proportion, give context, of US adults who correctly answer nitrogen. Now the context usually comes straight from the wording of the problem. And just do that. On a free response question, just go up, what's the context? The proportion who would answer correctly. There. All right. Calculate the point estimate. That's the middle. The point estimate is the middle of the interval. So this is based off of something plus or minus something. It's based off of, you average it out, average your minimum and your maximum. It's based off of 20%. Our sample came back as 20%. And then the margin of error is the plus or minus part. Plus or minus 0.025. So if you take 0.2 and minus 0.025, you end up with that. If you take 0.2 and add 0.025, you end up at that. All right. So that is how you find the point estimate and the margin of error. All right, next. If people guess one of the four choices at random, you should get back a 25% result. That's just by guessing. Interesting. Does this interval provide convincing evidence that less than 25% of all US adults would answer the question correctly? Yes. 25% is not in our interval. 25% is above our interval, which means the true proportion, more than likely, is in this interval, more than likely. We're 95% confident that the true proportion is here. So that means anything in here is plausible for the true proportion. So we can say all plausible values in the 95% confidence interval are less than 25%. Therefore, the interval does give convincing evidence that less than 25% of US adults correctly answered nitrogen. I'm giving some context, I didn't feel like writing it. And that's a confidence interval. Example 5, last example, and we'll do this one together. In this activity, we'll use the confidence intervals applet to learn what it means to say 95% confident. All right, so click here for the link. You can do this as well. Set the population proportion to 0.5, the confidence level to 95, and the sample size to 20. Let's do it. Here we go. Oh, reset. Okay, here we go. 0.5 for my true parameter, population proportion, 95%, sample size of 20. So, kind of rerunning this app again. We did this already before a little bit. First question, did the first confidence interval capture the true proportion? So we're going to take a sample, and we could use the formula in the form of the packet. Our sample came back as 55% plus or minus 22%. That would be the confidence interval based off of these criteria. Now, is every sample going to capture the 0.5? This one does. This sample captures the 0.5. 0.5 is in the middle somewhere. Okay. Did the first confidence interval capture the true proportion? Yes. Yes. Okay, repeat this 10 times. How many of the intervals capture the true proportion? Let's see. Let's repeat it 10 times. So that's 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. All of our confidence, all of our samples reported confidence intervals that did capture the true proportion. So we are 10 out of 10 for our sample proportions. That's pretty good. Next, reset and then take a total of 50 confidence intervals. How many of the 50 capture the true mean? Let's try it. So let's reset. do sample 25. And so, look at that. There's just some bad samples right here. It's okay, it happens. Sample number 25. So, of the 50 samples that we took, 48 of them hit for a 96% hit rate. This 25, all of them hit. All of them hit in this. The first 25, a couple of them didn't hit. Okay, so the question is this surprising? And it probably is not, because we got a 96% hit rate and we did a 95% confidence interval. We weren't guaranteed that each interval or each sample would create a perfect interval. What we did was we're saying that 95 out of 100 in the long run should hit the true proportion. Repeat step C, but do it 100 times. Okay, let's reset and we'll do it 100 times. 1, 2, 3, there we go. There's 100 and we got 97%. 97% of our samples created there was a bad one right there. This one just happens by chance. But in the long run, I got 97 out of 100. Again, we're not guaranteed perfect 100% hit rate. Whew, sorry for my camera work, I'm holding it right now. All right, watch your confidence intervals as you drag the confidence level from 95% to 100%. Don't reset. What happens to the intervals when the confidence level is increased? Does this make sense? Watch what happens. As my confidence increases, ooh, that was bad. Let's start at 80%. At 80%, I'm at a 79% hit rate. You can see some of my samples did not hit. As I go up to 90%, I increase the hit rate. As I go to 95%, it increase, and then that one didn't change too much. Let's add a couple more. Interesting. Okay, question is, where was I? What happens to the intervals when the confidence level is increased? As confidence level increases, I'll put you back on my stand here. As confidence increases, the interval increases. The width of the interval increases. There we go, look at that. As I increase, my width increases. Look how small my intervals are here compared to the width of up here. You get a wider interval, like my age. When I said is my age 35 plus or minus 2 or 35 plus or minus 10? Which one would you put your money on if you had to bet? 35 plus or minus 2 or 35 plus or minus 10? You probably have more confidence in your bet on 35 plus or minus 10, right? Because as confidence increases, the interval increases, and vice versa. As the interval increases, your confidence increases as well. So these kind of work both ways. They imply each other. Next, reset the sample 100 and an 80% confidence interval. How many of the intervals capture the true mean? I'll just do that real quick. Reset sample at 100. Dang, I just got 70%. Look at that. That's not very good. I just got 70% hit rate at the 80% confidence interval. How many of the intervals capture the true mean? Only 71. That is very low. That should not be that low. Interpret the confidence level. All right, so here's the script for confidence level. In this scenario, we would say in 80% of all samples, the resulting confidence interval will contain the true population parameter, whatever that is. Ours came back as 71%. That shouldn't have happened. It should have been closer to 80%. All right, but that happens by chance. All right, probability is a weird thing. This is just something that should have been. In fact, if I do it again, it should be. Let's just do it again because I don't like that. That shouldn't have happened. Let's try it again. Let's do 100. Let's look at the hit rate. Holy cow! It came back to 70 again. It should have been 80%. This is 80%, right? 80% of my intervals should be hitting. Let's do it again. I don't like this. There, that's better. I feel better about 77%. I bet if I do it again, it'll be more. It has to, right? Oh, it's a 77% again. 68%, that should not be happening. There, now it's 80%. There we go. This is how it should be. Interesting. Okay. All right, now we will see what happens when we adjust the sample size. Change the sample size from 20 to 100 and do a sample, and then change it to 250 and do another sample. So let's see what happens. All right, let's reset. And we'll change this back to a 95%. So this is 20%. And look what happens when I change it to 100. Ooh, my intervals get much smaller. My intervals get much smaller. With a larger sample size, I'm more confident in a smaller interval. Let's try 250. Let's look at. Whoa, look how small those intervals are. Again, with a larger sample size, I'm more confident in a smaller interval. Because with a larger sample size, there's less variability. With a larger sample size, there's less variability. So my interval can be smaller. All right. As sample size increases, variability decreases. Which means the standard error decreases, which means the margin of error decreases, which means my interval decreases. So all that kind of goes together there. As the sample size increases, the variability decreases, the standard error decreases, the margin of error decreases, and the overall interval decreases. All right, that is an introduction to confidence intervals. You have your assignment now. We will continue a confidence interval discussion next class. Happy E-Day.